In recent years, automation and robotics have become integral pieces in the advancement of the construction industry. The demand for architecture customization is continually increasing, as well as the need for more complex products. As we look to coordinate efficiency in the construction sector, we must optimize traditional principles to meet contemporary needs. For example, projects today rely heavily on manual control and human operator visual feedback, which leaves room for inconsistency and error. In addition, construction projects rely on the coordination and cooperation of multiple entities. Failure to properly coordinate can result in losses in productivity and safety. Construction optimization via robotics and automation can improve production rate and performance, and productivity analysis, all while lowering the health and safety impact on the workforce. A major stepping stone to usage of robotics and automation is interpreting the environment. In this project, we seek to use object detection to distinguish objects from the terrain. Furthermore, we strive to recognize automated machines to allow more fluid coordination.
Here is a rough idea of the items and methods we will use to accomplish various requirements in the identification of an object. The two items we require are the depth and RGB images seen in the circles, and the methods are the round edge boxes, covering calibration, spline and edge detection strategies, and the algorithms that use data from the RGB images and boundaries set by the depth images.
In order to analyze the segments against templates, we must first run the calibration algorithm. The calibration works by estimating the planar parameters. It converts the images taken by the kinect into point sets, and then from point sets a transformation matrix is created. Using the generated points and the transformation matrices, we reproduce the coordinates of a plane using the singular value decomposition.
In the case of an aerial view, a spline may be formed from the depth data. This allows for the detection of bulges that find high-value spots in the depth data with ease. From there, it is a simple interpretation of these areas as non-terrain for further identification as either a machine or an object that should simply be avoided. There is still a need to test and integrate this into the overall project, and there is a possibility of slow computation proving too cumbersome, so this may be replaced with a quicker process as research continues.
So far, we can detect and segment edges with range imagery in MATLAB. Our first attempt at partitioning objects required computing a gradient for the image. With this gradient, we can filter the image based on an edge score that is calculated using the sum of squares of derivatives. We can take this segmented image a step further by concentrating on specific blobs in the image and highlighting them. We've learned to do this one of three ways. We can add upper and lower threshold values, which will focus on objects within a range. We can also partition objects by displaying the logical negation of an edge image. Essentially, this algorithm references the segmented edges, converts the doubled imagery data into the binary values, and negates the results, making the edges false and everything within the edges true. If you display these areas, it highlights potential objects. And our third method is highlighting regions or potential objects based on depth discontinuities. In order to do this, we applied a gradation scale factor based on percentage differences in the image.
So we found out the best method for after all the researching articles and everything was the line moth algorithm method. And what it does is it detects 3D objects through integration of two data sources, include colored image cues and the dense depth maps. And we chose to incorporate the method they used to create each template by extracting for each modality a set of its most discriminate features from the corresponding reference image and by storing their location. This would help us to detect objects in real time and location in a more efficient manner because it would only record its most pertinent features and align the local neighborhoods exactly to the associated locations, unlike methods such as dot, HOG, or sift, which only are adjusted only to the regular grid. This feature is great in the sense that in the past it was done in a single modality, but they adapted this method into multiple modalities. We we'll apply some sort of gradient to filter the image using the template matching method based off of the method they used. If we're given more time, we'd further explore the method they used to recognize the objects. And as you can see from the image, they did use the gradient to detect the multiple modalities of the textureless object. And the second is the dense depth maps, which has been proven to be more discriminate and robust in eliminating change in noise. In terms of reliability, it's the most reliable for cues on textureless objects. It has normalized gradients and magnitudes and occlusions as well. It does not affect object recognition over dark or bright manners. And evaluations on the line mod algorithm evaluation is that it is one of the best methods for generic rigid object recognition and proceeds using very fast template matching. We generate templates by using this package that contains a small library to generate random views around the object. The input is given through a mesh, and views are generated according to certain boundaries, angles, scale, in-plane rotations, etc. And the outputs are for the depth, RGB, and mask. And all of this can be learned online, unlike statistical learning techniques. However, it lacks performance in hugely cluttered environments, so additional modalities will have to be utilized to improve the performance. This method is extremely helpful because it helps detect objects in difficult environments such as construction sites. The article use of the image integration aligned with our problem because it shows abstraction gradients from color images, which have become more robust to background and gradients and grayscale images.
Now we know that we're able to detect edges as well as object regions. Moving forward, our next step is interpreting these regions and estimating dimensions and distance. As mentioned previously, the line mod algorithm may prove useful in recognizing objects, and more specifically, our construction machines. We plan to implement a template matching algorithm similar to line mods. Essentially, we expect to pick a position near where we expect the vehicle to be in the image. Then we apply a gradient filter based on a template of the potential machines. If the template moves over the expected region, then we've found a match and our object recognition is successful.
As this is part of a larger continuing project, we hope to include future features, such as preliminary planning, incorporation of digital models, and incorporation of variable objects. Preliminary planning would be to map out areas in response to detected machines, allowing for safe moving areas or areas where certain functions take precedence. This could be enhanced through the use of digital models describing the exact shape and size of a detected object and its movements, and could be readily found via visible tags placed on machines or environment cues. In the case of machines where the shape can be altered, such as the pictured robot arm, the problem of detection and accurate space management increases, so further research would be required.